All you people at home, pause the video and get this copied. All right, so hey, we have tackled 2 out of 5 lectures in reactions. And in those 2, you've learned how to translate. If I give you a sentence, you can write symbols, right? Reactants yielding products. And once you have that sentence, you are able to balance it. Make sure that there is the same number of reactants and products. Hopefully you're feeling pretty good about that. The other 3 lectures are a bit different. It's still reactions, but they are connected in a different way. Here's what your objective is for today, tomorrow, and Monday's lecture. There's 4 types of reactions that I want you to learn about. And there's 2 things. 2 things I need you to do for each of them. First off, you need to be able to identify them. If I give you a random reaction, reactants and products are just reactants, you need to be able to say that's synthesis, or that's decomposition, or redox, or precipitation. That's the more important of the 2 skills. What am I looking at? And I'm about to show you how to start doing that. The secondary skill is, once you know what you're looking at, how do you predict the products? Oh, that's decomposition, so I know I need to do this, and I'll know what those 2 reactants will make. It's actually pretty cool chemistry, because when the zombie apocalypse eventually attacks us here in about 3 months, and you are living in a camp outside the city with a bunch of strangers, and they're suddenly like, we need hydrogen peroxide or his leg's going to fall off. You might be able to be like, oh, well, if we mix this with this, we would get hydrogen peroxide. Are you ready for that kind of responsibility? Maybe. It's cool chemistry to know. So we're going to knock out 2 of the 4 reactions, because the 2 we're not doing today get a bit twistier on figuring them out. So these are the 2 easier ones, in my opinion. So the other 2 get their own lectures. So today, we're going to figure out how to identify synthesis and decomposition. And once you've identified them, how do you predict the products? You ready? Take a look at synthesis. You've heard the word synthesize before. To synthesize something is to take parts and build them, put them together. If you look at the A plus B stuff, this is a skeleton reaction. So it's basically saying that you'll have a substance reacting with a substance, and it's going to make a new substance, but it's made up of those. But more importantly, for synthesis, you'll see that there's only one product. In a synthesis reaction, there won't be any plus signs on the product side, because it will just make one product. All right, so then what are those reactants? Well, if you read that screen, you'll see they can be one of 2 things. It can be a free element reacting with a free element, and you'll push them together, or more trickily, it can be a compound reacting with water. And water is a compound, so it's a compound with a compound. But that's the other way to recognize synthesis, is a compound reacting with water, which I'm going to show you examples. So we want to be aware of the 2 ways that this can look. So let's check it out. Write down our first example, please. Remember, the most important part of any random reaction is what the heck am I looking at? So really hone in on the way I think about it. Look. There's a free element above my hand. Do you agree? Another free element. Yes, there's 2 of them because it's diatomic, but that's because it's a free element. If it's a free element and a free element, it's automatically synthesis. So what are we going to do? Push them together. On the other side, Mg and O, just like that. But sir, what about the 2? The only reason oxygen has a 2 over here is because he's a free element and diatomic for reasons that you should be really good at by now. Over here, you made a compound. So don't automatically bring subscripts over. follow the chemistry that you know. Now, you made a new compound though, so just like you always do when you translate, when you predict, you still need to check this stuff. You made a compound, therefore you need to check the nomenclature. Metal, non-metal, ionic. You have a periodic table in the back of your packet, right? Make sure you know how to check oxidation states. We've got +2, -2, so nothing's going to happen. But make sure you check. So that's the whole thing. Now, if you want to be a good scientist, you should balance it. I don't have time to make lists or reteach balancing today. Hopefully, you're getting good at that. But an unbalanced reaction is always kind of wrong. So even if a question doesn't ask you to balance, you should still be balancing. But anyway, I'll balance most of the examples today automatically. Let's do another one. I didn't write down the Roman numeral because technically it doesn't belong there. It is essential info because iron can have multiple charges, which could be important on the other side. But whatever, if you wrote the Roman numeral, it's fine. Let's go talk to somebody. Let's go over to cluster 3, C2. Hey, 3-2. This blue reaction is synthesis. How do I know that? 2 free elements, yeah. Free element plus a free element, synthesis. So we follow the synthesis rules. Push them together. Don't automatically bring subscripts, right? That's there because it's diatomic. Now it's a compound, different rules. Ionic, metal, non-metal. Now that Roman numeral, for those of y'all at home, you can't see, there's a Roman numeral 2 on the projector. Anyway, +2, -1 if you check the oxidation states. So there will be a crisscross, right? A 2 is going to cross right there. It looks like bromine brought his subscript with him, but he didn't. It appeared for a different reason. It's being deceptive, but it's a 1-to-1-to-1 mole ratio. That's half of synthesis. Those are easy ones, and I'm going to give you easy ones, so don't forget they exist. But the harder ones are the ones that are a bit more annoying. Write down the next example. Look back at the opening slide. Look back at the notes you wrote in the dark. And you'll see there's another type of synthesis. There's free element, which you're now good at. But there's also compound plus water. Look. See how that's compound? Multiple elements? See how it's reacting with water? Synthesis. One product, but weird synthesis. Here's what I need you to do. In your packet, by the way, at home, get out your reactions packet. Near the middle of the packet, you will find a synthesis decomposition page. Find this paper. It says synthesis decomposition near the middle. And we're going to look at the synthesis. If you don't have it at home, pause the video and copy down the synthesis section. Now, if you look at that section, you will see that the first 2 sentences there repeat stuff I've already said. It's the last 2 sentences, 3 and 4, that we care about. Focus in on this so it's not hard. whenever, at least in this class, all right, there's chemistry outside of this. We have a little bit of tunnel vision here, but it's good practice. Whenever you're doing the compound with water synthesis, you need to focus on this dude right here, because one of two things will be true. He'll either be metal or he'll be non-metal. And based on that fact, one of those two weird rules that you're looking at in the packet are going to activate. Sodium, is he metal or non-metal? He's an alkali metal, right? So we're not going to follow that rule. We're going to follow the rule about metal oxides, which is the third sentence on the packet. Does everyone see what I'm talking about? And y'all, it flat out tells you what to do. All right, it's weird, but it holds your hand. And it says, if you have a metal oxide reacting with water, the product is automatically metal hydroxide. Wait, metal what metal do you think this problem is referring to? So yeah, the only metal in the problem. All right, I always lose students. They're like, well, I don't know what metal to pick. There's only one metal in this question. It's sodium. So over here, put that metal and bond it to hydroxide because it says so. Of course, hydroxide's polyatomic. Look it up if you don't know it. And that's it. You did it. Now check it. When you do, you'll see it's +1, -1, so nothing happens, but make sure you check it. Now I know it's weird, but it's what happens in nature, and you just read it off the packet. Metal oxides form metal hydroxides. Let's do another one. The identity is the most important part. Look, compound reacting with water. Synthesis, there will only be one product. Magnesium, what is his identity? Metal or non-metal? Alkaline earth metal, also a metal. So it's the exact same stinking thing. Let's go over to cluster 3 again and talk to seat 2 again. 3-2, you are my friend today. What should that product be? Yeah, you take the metal, magnesium, and you put it with hydroxide because that's exactly what the rule says to do. Check the product. It's a compound and it's ionic, metal to polyatomic. Hey, but look, there actually is interesting oxidation here. It's +2 -1. So the 2 is going to cross to a polyatomic ion. Make sure you are on top of all of your chemistry. What do you think so far? But there's still a synthesis rule we haven't gotten to yet, right? Let's do another one. Identify the type of reaction. Compound reacting with water. Yeah? Synthesis. But how would you describe that dude? Carbon is a non-metal. Remember, it's to the right of the invisible staircase. Know how to find that. So look back at your packet. Look at the packet you copied. All right. And you'll see that the very last fact talks about non-metals. So let's see what it says. It says non-metal oxides with water in synthesis form Oxyacids. So that's a new vocab word for you. Oxyacids. This is still easy. If you remember this, what element do acids start with? Hydrogen. Ooh, good job. That was several months ago. All right. So we know that acids automatically start with H. So whenever you do have the nonmetal happening and you know this is going to be an acid, you're going to start with H, and then here's how you build the oxyacid. You're going to drag all of the non-hydrogen stuff over there, and you're done. I'm going to drag all of the non-hydrogen. Look here, carbon, carbon. 1, 2, 3 oxygens, 3 oxygens. Little different than the way we've done anything, but building oxyacids do that. And you're done. This only happens when it's a non-metal oxide here, because your paper says so. But check what you wrote, right? We got a new thing over here. So hydrogen is +1. CO3, this item we built, is actually a polyatomic. It's carbonate. -2. Crisscross. We're hoping that's a good silence. Let's do another one and we'll be done with synthesis. It's a compound reacting with water, so it's synthesis. One product only. Again, sulfur is a nonmetal. So look at the packet, follow the rules, and your one product should be an oxyacid. Acids always start with hydrogen. And then just bring over the non-hydrogens. 1 sulfur, and 1, 2, 3, 4 oxygens. Let's go over to cluster 3. There's no stinking way that it could happen. Cluster 3, seat 4. Hey, 3, 4. We made sulfate here. What is sulfate charge? It's polyatomic. You have it at the front of your packet. -2. So the 2 will cross down here because hydrogen is a 1. Are there any questions? And that is half of today. Yeah. All right, let's move on to our second type of reaction. Decomposition. If you look back at your opening screen and look at the skeleton for decomposition, you'll see that all it really is a flipping of the arrow. If you reverse that yield sign, this reaction becomes this reaction. In other words, decomposition is just the opposite of synthesis, right? Breaking apart instead of building. Just like synthesis, these can be very simple, which we'll start with, or fun little twists. So let's see if we can break apart compounds instead of build them. Here we go. Of course, the most important part is, what the heck am I looking at? How do you know it's decomposition? Well, only decomposition has no plus signs on the reactant side, if you want to say it at a low level. All right, one reactant. That's the trick, is that there's only one reactant, and you know it's automatically decomp, so we follow decomp rules. So what do? Well, if it's decomposition, break it apart. Over here, we've got mercuries, we've got oxygens. Check what you wrote. Little different this time because we made free elements, so we need to check diatomics. Is mercury diatomic? Nope. Is oxygen? Yep. And boom, we're done. I mean, we could balance, so I know I haven't been balancing all of them, but it's a good habit. Let's do another one. Go over to cluster 1. Talk to seat 5. Hey, 1-5. Hey, 1-5. This is decomposition. How do I know that? Because there's no plus sign, right? If there's only one reactant, then it's decomposition. And in this case, split it apart. I made free elements. Are they diatomic? Neither of them are a part of Brinkelhoff, so leave it be. Decomposition's easy, yeah? Don't forget these easy ones exist. I've noticed that like near the end of the unit, the harder ones I'm about to show you, anytime decomposition shows up, you try to do all this extra stuff. All right, if there's no extra stuff to do, don't do it. But look at your packet. There is also a decomposition section of the packet. If you don't have it at home, pause and copy. The first two things printed there, again, repeat things I've already said. It's sentences 3, 4, and 5 that you might want to put a big star next to or whatever, because you will want to refer to them often. Those go over the funky things. So let's look at it. Write down our next example. I know it's decomposition because there's only one reactant. However, CO3 is one of 3 substances that sets off an alarm for me. Carbonates, hydroxides, and chlorates are what to look for. Are there other weird things out there? Yes, but we only cover so many of them in this class. We care about these 3 that we want you to know. Carbonates do weird things, but it's easy because just look at your packet. Look at the third sentence under decomposition and let's see what it says. It says that metal carbonates decompose into metal oxides. All right, it says metal bonded to oxides and carbon dioxide. Those are the 2 things it says that you're going to always have. What metal? What metal? What metal? What metal? What metal? What metal? The only metal. That's not tricky. It's ridiculously easy. You don't even have to pick between metals. Only one metal. Sorry, I've been teaching this long enough and it's just I get it all the time. I don't know what metal to put there. Calcium. The metal should be calcium bonded to oxygen along with CO2, carbon dioxide. And there it is. That's what happens in nature. Just follow the paper to know it. Check what you wrote. Calcium oxide is an ionic compound, but it's +2, -2 when you check those predicted charges. So let's do another one. I know it's decomposition because there's no plus signs on that reactant side. Uh-oh. It's one of my weird dudes. Let's go over to cluster 3, seat 1. Hey, 3-1. What will the first product be? Aluminum with oxygen. Yeah, aluminum oxide. The metal, as your rules say, followed by oxygen, always. What's the other product, anybody? CO2, because it always is when carbonates decompose. Check charges of him. You don't have to check him because it says carbon dioxide and that's covalent. You probably die. You've probably already done it. All right. But check those charges and you'll see that it's +3, -2 in crisscross. Yeah. What happened to it? It broke apart into other stuff. Chemically, it broke apart into other stuff. Then you would balance it to account for stuff. But that's the exact thing, is instead of me trying to track this moves here, this moves here, just telling you the constant products of a decomposing carbonate. When this crosses, you'll get a final compound that looks like that. Now, as you can see, there are 2 other decomposition things that can happen. And we're going to go over them, but it's the exact same thing. If you can read what's on the paper, then you know what to put in the answer. So let's check it out. I know it's decomposition because there's only one reactant, but see the OH? That's hydroxide. Hydroxide is another one of the 3. So look at your stuff. There's a hydroxide rule, and it reads, metal hydroxides decompose into metal oxides. The only metal here is potassium, metal oxides, and what else? Water. So now when that zombie thing happens and you're like, oh, we have this potassium hydroxide around here, you can be like, dude, let's break it apart. There's a little more to it than that, but I want you to be useful. This is the decomposition of hydroxides. Check him. You don't have to check him. You memorize that's what water looks like. But this is going to be +1, -2. So make sure you do the nomenclature. Are y'all disagreeing on whether it's fun or not? It's kind of boring, I guess, but you're getting smarter. All right, last example before your self-practice. This looks fun. You're sick of me saying it, but it's the most important part. I know this is decomposition because there's only one reactant. Follow decomposition rules, but ClO3, if you look it up, is pronounced chlorate, which is the final decomposition rule. And it says that when the chlorates decompose, they always make metal chloride. That's a little different. Metal chloride. So there's the only metal that we have, all right, followed by chloride, so a bonded chlorine, following the words, and what else? And oxygen, which some of you might still write like that. It's fine if you're still going step by step. But of course, oxygen's diatomic. You can check it all from the free element. But check him also. Chlorine is +3. I'm sorry, aluminum's +3. Chlorine's -1. If you are still really bad at that oxidation state, Fang, my tutoring is tomorrow at 8:05. What do y'all think? Think you can do some by yourself to end class?
I don't think we can.
Ah, that kid wants to come do it in front of everybody. All right, Mr. Featherstone, if you could, I'm just kidding. All right, I want you to flip to the back of the page you've been staring at. Flip to the back of the page that you've been staring at. And what you'll notice are these examples that are now being projected. All right, so you don't have to look up there. You got them right here. I'm going to give you a little chunk of time. Take 7 minutes and get as far as you can get. There's nothing new here. It's just mixed practice. Talk to a shoulder buddy if you need to. All right, if you get stuck, ask for help. Predict all the products following what we've done today. I mean, always you should, but like for time purposes right now, get everything predicted, and then if you have time, you can do that. Go slow. If you get stuck, look at our previous examples, right? We did all of these types in class today. You got this. Watch your nomenclature. Anytime you create a new compound on the product side, check it.
Aiden, you get the last one. I didn't do the last one. Not there yet. Leave me alone. I work slow, bro. You should see me in algebra. It's pretty bad.
You stay through that way.
I'm about to show you. I mean, I'll show you the answer. I'm about to reveal all the answers at once up here. Oh, I forgot about y'all. I'm sorry. I'm about to reveal all the answers. If you're still working, you can ignore them. Don't look yet, but here we go. When they pop up, if you got something different than me, then speak up, ask about it. Or, I mean, unless you know the mistake you made. But we can talk about these. How'd you do? I didn't balance any of these.
I knew it. Oh my god, I knew it.
Oh, does it?
Oh my god.
Oh, on the packet it does? Yeah, that's not supposed to be there.
I've never listened to this ever.
I'm sorry, because that's because it is part of balancing it. Sorry, I didn't realize that was there. I mean, if you balance it, the two will appear. See how there's two of them over here? So you would need two of them there. I don't know. Apparently, I copied it from a balanced.
Jayla hits me. She hits me. She berates me. She's a bully.
Yep. On the first one? Hey, here, just ask it out loud. Okay. Yeah, but it's a metal. You only make it an acid if that's a non.